Today we start with the linear algebra problem. So the first problem is given that suppose S and T two linear operators from R3 to R3. So S is a function from linear transformation from R3 to R3 defined by S of x comma y comma z equal to x comma x plus y comma x minus y minus z, and T is another linear transformation from R3 to R3 defined by T of x y z equal to what is that, x plus 2z comma y minus z comma x plus y plus z. Okay, so then which of the following is true? So the first option is S is invertible but not T. S is invertible means what? Both 1 1 and on 2, then we say is invertible. S is invertible but not T. This is the first option. Then second option is T is invertible but not S, and both are invertible. Both T and S are invertible. That is the third option. And fourth option, neither S nor T invertible. Neither S nor T is invertible. So how to check the function is the linear transformation invertible? We have to check it is 1 1 and on 2. So how to check 1 1? So simply the kernel of the map is singleton 0. If the suppose kernel of the map it contains only 0, that is 0 comma 0, only 0 if and only if S is 1 1 map. If you take any linear transformation, the kernel contains only singleton 0, then the map is 1 1. And when we say the map is onto, the image of the linear transformation should be the whole codomain. Okay, that is rank is 3. If in this case rank is 3 in this case. Now look at the first thing, S. What is kernel of S? And then you can rank nullity theorem, you can find the rank of this. So kernel of S equal to collection of all ordered triples such that S of this should be 0. 0 means actually 0 comma 0 comma 0, and that is our collection of all triples x y z. What is x plus y plus x comma y comma z? Nothing but x comma x plus y comma x minus y minus z. It should be 0 0 0. Now this ordered triples are equal, then we can compare the each coordinate, therefore we get x equal to 0 from the first one. Since from the second coordinate x plus y equal to 0, already x equal to 0, therefore y should be 0. Since x y is 0, if you substitute in the last coordinate, z should be 0. Therefore only z, only 0 comma 0 satisfy the condition. Therefore since the kernel contains only 0 0, therefore the map, the linear map S is 1 to 1. By rank nullity theorem, dimension of the domain is 3 equal to nullity, that is nullity of S plus rank of S, but null space contains only 0, therefore dimension 0, therefore rank of S should be 3. Since rank is a subset of codomain also R3, the dimension is 3, therefore the image, the range space should be, or the image of the space should be the entire R3, because both have dimension 3, therefore this is equal to this one. So from this we can conclude that S is onto. Since S is 1 1 and onto, therefore S is bijection, that is invertible. A linear map is invertible if it is both 1 1 and onto. Now similarly for T, so first you have to find the kernel of T. So kernel of T is collection of all x, y, z such that T of x, y, z is 0. 0 means 0, 0, 0. And by the definition of T of x, y, z is nothing but x plus 2z comma y minus z and then x plus y plus z equal to 0, 0, 0. So any doubt? Okay.
Sir, can you once again repeat that on to how, sir?
By rank nullity theorem, the rank is 3, right? So what is actually rank of S means what? Dimension of the range space. Dimension of the range space we define rank of S. So sometimes called range space or image of the space. Here we showed that this is 3, rank 3 by rank nullity theorem, because this is 0, because the kernel is 0, therefore nullity is 0. By rank nullity theorem we get rank is 3, but rank is nothing but dimension of the range space or image space. But this image of the set is a subset of R3, okay, be codomain, because codomain also R3. Since already we know the dimension of this also 3, now we prove the dimension of this also 3, both have same dimension and this is subset of this, therefore the only possibility is both are equal. So both are equals means what? So what do you mean by onto? If you take any element in the codomain, we got to find a pre-image. So because since the range space is entire R3, therefore we can pick any element here. Suppose if you take some element Z, okay, suppose if you take some pick T, then T should be of the form S of something, because R3 is nothing but image of S. So image of, what is the definition of image of? It's collection of all S of capital X, where capital X in the R3. And we prove that this is equal to R3. Therefore, if we take any element in R3 is of the form S of something, therefore it should be onto. That's it. So proving a linear transformation or proving a function is onto, we have to show that the image of the set equal to the entire codomain. If you prove that, function is onto. Now here the image is our range space or image should be R3, therefore is onto. Now look at the kernel. This is the definition. So from this, if you compare the second coordinate, y should be equal to Z. Now we get y should be Z. And if you compare the first coordinate, we get x equal to minus 2z. Okay, but minus 2z might be minus 2y. If you want, you can do everything. So in the last coordinate, we have x plus y plus z equal to 0. Okay, so we can express x equal to minus y minus z, but this is nothing but minus 2y. Already we proved that x equal to minus 2. Therefore, we can replace everything in terms of, if you want, y. So otherwise in terms of x. Anyway, only one variable. Okay. So if you suppose you replace x equal to minus 2y, you can keep y, and then z is nothing but again y. Okay. So therefore, where here y varies in R. Now we reduce the number of variables. So if you take if you take y outside, we have minus 2, comma 1 plus 1, comma 1. Okay. So these elements always satisfy this equation. Okay. So we have at least one non-zero solution to this equation. So therefore kernel is not singleton 0. So since this is not equal to singleton 0, 0, 0. Okay. Okay, so at least one non-zero triple satisfy this one. At least one non-zero element in the kernel, therefore kernel is not equal to 0. Therefore, since kernel is not equal to 0, therefore the map T is not 1, 1. So since T is not 1, 1, you can easily say that T is not invertible. So invertible means both 1, 1 and 2. So here we know that is not 1, 1, therefore is not invertible. Therefore S is invertible but not T. So that is the option, correct option. So the first option is correct. So S is invertible linear transformation, but T is not linear invertible linear transformation, because S is 1, 1 and 2, but T is not 1. Okay. Now next question from linear algebra. Second question. Suppose we have a 3 vector space. Suppose V, W, X are finite dimensional vector space. Every finite dimensional vector space, and such that dimension of V and then dimension of X equal. So dimension of the vector space V equal to dimension of the vector space X. Suppose both dimension is equal, it is given, and suppose S is a linear transformation from V to W and T is a linear transformation from W to X. These are all linear transformation, and such that what is the condition between this S and T? The composition T composition S actually is a function from V to X. So domain of V is nothing but domain of S is the domain. So domain of S is V, therefore this one. Codomain of this is the codomain of capital E. Codomain of capital E is X. Therefore the composition is a function from V to X. Okay. Now it is given that is 1 1 or injective. So it is given that the composition is injective, that is 1 1. So the composition is 1 1. These are all hypotheses. Now what is which of the following is true? Suppose the first one is S and T both are 1 1, injective or 1 1, 1 to 1. So second option is, so S is 1 1, S is on to, T is 1 1. So S is a on to linear transformation and T is a 1 1 linear transformation, and then both are 1 1. So S, both are on to. And then the last option is S is 1 1, T is on to. S is 1 1 linear transformation, then T is on to linear transformation. But it is given that T composition S is injective. Okay. So how to prove this one? So I already said that if the composition of two functions is 1 1, then the first function should be 1. So we have to use that one. So anyway, so we try to prove S is 1 1. So how to prove S is 1 1? Suppose S of X equal to S of Y, we have to prove X equal to Y. To prove S is 1 1, if suppose the images are equal, then the element should be equal. Now suppose take S of X equal to S of Y. Now apply T both sides. Therefore T of S of X equal to T of S of Y. But T of S of X is nothing but T composition S of X by the definition of composition, and this also T composition S of Y. Since T composition S is 1 1 and this is happened, therefore from this we can conclude that X should be equal to Y. So therefore S should be 1 1. S is 1 to 1. So since S is 1 to 1 and is given the dimension of since S is 1 1. So already we know that if S is 1 1, what can you say about the kernel? Kernel of S should be 0, because linear transformation is 1 1, the kernel contains only trivial element. Since S is a map from V to W, okay, since we know that S is a map linear transformation from V to W, and here what can conclude about since by apply the rank nullity theorem, we have dimension of V should be rank plus nullity. Anyway nullity is 0 here, anyway it should be rank of T. So R of T we can write R of T, but R of T is nothing but dimension of range space of S. So dimension of image of S. Okay, we know this one. So now we can talk about the T. So T is a function from W to X. Is given that T is a linear transformation from W to X. Now we know that dimension of V, so equal to dimension of X is given. Okay, so dimension of X is given that equal to dimension of V. Okay, and this should be equal to range of t, okay, because using this relation. So this is given, but dimension of v equal to dimension of this one, that is nothing but we can say okay, r of t. Okay, now so what is actually r of t? So maybe you can see, even you can write, so r of t is nothing but dimension of image of the linear transformation S. But now look at here. So that means what? This actually image of S is in subset of the codomain W for the linear transformation S, because S is a linear transformation from V to W. Therefore the image of S should be contained in W. Therefore image of S is contained in W. Therefore since this is subset of this, therefore the dimension of this less than or equal to dimension of this. Therefore this is less than or equal to dimension of W. But what is the dimension of image of S? Is nothing but we call R of S. Sorry, R of not T, is everything is S. Rank of S is the number, that number should be less than or equal to dimension of V. So dimension of V is bigger. But just now we proved that this is nothing but dimension of X. Dimension of V, but dimension of V is nothing but X. Now what we have? So we heard here dimension of X is a codomain should be less than or equal to dimension of W, either equal or strictly less than. Okay, but from this what can conclude? Either we can prove that T is onto or not. So anyway, the domain dimension is more than the codomain dimension. Okay, so is T is 1 1? So question is the function T is 1 1 or not? So suppose T is 1 1, what you will get? Dimension of the domain by rank nullity theorem. Dimension of the domain equal to T is 1 1, then kernel is T is 0. Therefore we get dimension of the image of T. But dimension of image of T is less than or equal to dimension of X. The X is a codomain. But here we get should be less than or equal to, but we know that dimension of X is less than or equal to dimension of W. Therefore T cannot be 1 1. If T is 1 1, we get this one. Okay, so we cannot say T is 1 1. So therefore S 1 1, but T is not 1 1. But what can I say about onto? Maybe we can say directly say that onto, because okay, we can say it's an onto function, because dimension of X. So usually because the codomain dimension is smaller than domain thing, we can define the onto function. Usually suppose the domain contains a small number of elements, but the codomain contains more number of elements, we can define 1 1 function. Okay, so similarly say suppose we have two sets A B. So using the set theory, suppose the cardinality of A is n, and then the cardinality of B is m. If n is less than m, then we can define 1 1 function from A to B. If the domain contains small numbers and then codomains contains more numbers, then we can define 1 1. But if you take domain is B, codomain is A, we cannot define 1 1 function. No, we cannot define 1 1 function. Okay, so 1 1 means what? Always domain should be, if you take the finite set. Okay, so similarly, if for onto, the codomain contains small number of elements and then domain contains more number of elements, we can define onto function in the finite set. Okay, so same thing, or I did any mistake, so maybe I erase, maybe yeah, T maybe I think 1 1. So we try to prove T is 1 1. Okay, I think maybe because this is less than or equal to, and this is sometimes if it is equal, then this is satisfied. Okay, maybe we try to prove. I think it's maybe happen. T is 1 1. So how to prove T is 1 1? So maybe we can apply. So because already we know that S is 1 1, right? So maybe yeah. So maybe T is 1 1 because the dimensions are equal. So that's why. So S is 1 1 is clear, right? Because we can directly prove using the assumption take thing. Now we try to prove T is 1 1. Why T is 1 1? You have to use that dimension of V and the dimension of X is equal. Okay. So maybe it takes some time, but okay, we because it's given that dimension of V equal to dimension of X, that is important thing.
Sir, we know that T composition S is 1 to 1.
Yeah.
So we can say that dimension of V is greater than or equal to dimension of X.
Dimension of
V is greater than or equal to dimension of X.
yeah, it is clear. It is given that actually equal, because in the problem itself is given that dimensions are equal.
Yes, sir, it's good.
Yeah, okay. Therefore, it's actually onto. It's become onto since both have dimension equal. Okay, and it's 1 1. Maybe you will get equal. That is sorry onto. The T composition maybe is onto. No.
It will be bijective, no sir, because dimensions are same, and if it's onto, then it will be bijective.
No. Okay. So you see, you are saying onto. So T composition S is a function from V to X. You are saying is already we know that 1 1. So therefore you are saying is onto. Why is not onto? Because anyways both have same dimension. Okay, but same dimension and then it's 1 1. So therefore dimension of we can say is onto, because by rank nullity theorem dimension of V equal to the null space of the composition of a linear transformation plus rank of the composition, the operator. Okay, by rank nullity theorem. But this is 1 1, therefore this should be 0. Null space dimension should be 0, and there should be a rank of the dimension of the images space S T composition S. Okay, this is nothing but dimension of the image of the space T composition S. This is dimension of V, but dimension of V is given the dimension of X. Okay, so therefore the dimension of image is a subset of X. Okay, both are same dimension, therefore image of the operator should be equal to X, because both are same dimension, and this is subset of, usually the image of this should be a subset of codomain, and both have same dimension, therefore should be equal. Therefore since the image is contained, image of this one is equal to entire codomain, therefore the composition is onto function. And already we know that if the composition of two functions is onto, then the second function is onto. So implies that T is onto. We can easily prove it. So how to prove this T is onto? So if we draw the picture Venn diagram, we can easily look at this. So suppose we have a vector space V, and then another vector space is W, and then another one is X. Okay, so we have a linear transformation S from here to here. So S is a linear transformation, and another linear transformation from here to here is T. Now the composition is a function from V to X. Okay, so the composition is a function from V to X. This is a T composition S. It is given that is onto. So now we have to prove that T is onto. That means what? Given any element here, we have to find a pre-image to match to that element. For to proving T is onto, okay. So we start with an element some X here. So we fix some X. So we pick X in X. So what is our aim? Find some W in W here this w max to x under the function x. So such that t of w should be x. That is our aim. X. But we start with the x in x. But we know that this t composition S is onto. Therefore, given any element here, we can find a element v here. This v maps to x under this function. Okay. So since this t composition S is onto function from v to x, and you are giving x in x, therefore there exists some small v in capital V, such that this map t composition x act at v maps to x. But what is this t composition S? Is nothing but t of S of v. Okay, this is equal to x. Since v is here and S is a function from this to this, therefore this v maps to somewhere, that is S of v, and this S of v is our required w. We choose, so let choose w equal to S of v. Now what is t of S of x? We know that x equal to t of S of v, but we call is w, therefore t of w. Now we got t of something equal to x. That is our aim. We have to find the w in w such that t of w equal to x. Now the w is nothing but S of v. Okay, therefore t is onto. Therefore t is onto, and S is 1 1. So that is the correct answer. T is 1 1 and S is onto. Okay. So any doubt in this? Okay. So next question from real analysis. Third question. Suppose f is a function defined on open interval 0, 2 to r, the entire r, defined by f of x equal to, in the interval, if x is rational number, we define x square. Okay, so we define x square if x is rational. If x is rational number, we define x square. If x is irrational, we define 2x minus 1. 2x minus 1 if x is irrational number. Now which of the following is true? So first one, f is differentiable exactly 1 point. So differentiable exactly 1 point. Exactly at 1 point. And then second option, f is differentiably exactly 2 points. So f is differentiably exactly at 2 points. And then the third option is f is not differentiable. F is not differentiable at any point. Any point in this interval 0, 2. And then f is differentiable at every point. F is differentiable at any point in this interval. So which one is correct? So whenever a function is differentiable, first of all that function should be continuous function. Without continuous, we cannot talk about the differentiability of a function. Okay, because we know that every differential function is continuous, right? So therefore that function should be continuous. Suppose you are talking about differentiability. Now we know the method to check which point the function is continuous. You have to equal these two. So x square should be equal to 2x minus 1, and if you take this side, we get x minus 1 whole square equal to 0. If you solve, we get x equal to 1. So therefore the function is continuous only at x equal to 1. Okay. So therefore if it is differentiable, maybe it's possible differentiable at 1 point. Therefore we can omit option B, because we say differentiable at 2 points. If it is differentiable at 2 points, then it is continuous at 2 points, but we know that continuous at only 1 point. So therefore it should be exactly differentiable at only 1 point. All others are wrong. And then the differentiability is 2x and then 2. if we say x is irrational, the derivative of a function at a irrational point is 2, at a rational point is 2x. It is differentiable only at only one point, because it is continuous at only one point. Okay.
So normally how can we find if one function is continuous or not, sir?
This type of function, suppose they defined if defined some rational points goes to somewhere, for irrational goes to somewhere, we have to compare these two and then solve x, and if you find the x, that is the only point the function is continuous for this type of function, not for general function. Okay, for general function you have to use the definition, or you can use the sequence proof. Okay, so what is the sequence definition for continuity? Suppose we say f is continuous at x. Suppose we say f is continuous at a point some a or x. So when we say a function is continuous, there are so many definitions. So the first one is, suppose if take limit, or if you take better take some a. So continuous at a point a. So if the limit x goes to a f of x, if you take this, if this is equal to f of a, then f is continuous at a. This is the first definition. This is one of the definition using the limit. So limit x goes to a, sorry, x goes to a, f of x equal to f of a, then f is continuous at a. So this is the first definition. Or you can use the epsilon delta definition for every epsilon greater than 0, there exists a delta greater than 0, such that if you take any x, for any x in that set, whatever set you are taking, for any x with the modulus of x minus a is less than delta, implies modulus of f of x minus f of a, everything is equivalent definition. Okay, is less than epsilon. Okay, for every x around this neighborhood of a. This is another definition. And then the sequence definition is very useful one. So what is the thing? If you take any sequence xn, such that suppose xn converges to a, if you take any sequence converges to a, implies that f of xn converges to f of a. So the function is defined at a point a. Okay, you know the values of f of a. So if you take any sequence xn converges to a, if f of xn converges to f of a, then f is continuous at a. So maximum we can use the third one for general function. Using the sequence definition is very powerful. We can easily work with the sequence. Okay, if you go epsilon delta definition is very little hard, but if you go with the sequence or the limit, you can easily check the function is continuous or not. Okay, so suppose the function is not continuous, how to prove the function is not continuous? You can find the sequence xn which is converges to a, but f of xn does not converges to f of a, then function is not continuous at that point a. Okay, for proving continuous you have to take arbitrary sequence xn converges to a, proving we have to prove f of xn converges to f of a, but so f is not continuous, you have to find a sequence xn converges to a, but f of xn does not converges to f of a, converges to somewhere. So that is a main thing. But in this case of rational irrational, this is a trivial thing. Either you can use a sequence proof also to show that this function continues only at 1. You can use the sequence proof. But I say that method are just a shortcut to say that you have to compare these two and then say find the points. You can find the point x equal to 1 using the sequence definition also. Okay.
Okay, sir.
So okay. Next problem. Suppose the set V equal to, okay, another thing is there. Okay, suppose there are two subspace of R24. Suppose S is a, okay, don't use S because already we use this notation for linear transformation. Suppose we have a two vector subspace V1 and V2, both are is a subspace of R power 24 subspaces. Okay, there are two subspaces and then dimension of the one subspace is 19 and then dimension of the other subspace V2 is 17. This simple question. Then the first option, the smallest possible value for dimension of is 2. Okay, that is dimension of the intersection of these two is 2. The second option is the largest. Okay, so I am saying the smallest possible, therefore the smallest, at least should be 2 and maximum 18. So dimension of V1 intersection V2 maximum 18, minimum 2. And then third one is again the smallest one for the sum of the thing. So V1 plus V2. So dimension of this subspace, the largest value, the minimum value is at least 19. The largest value is V1 plus V2. The largest possible sum dimension should be 22. So which one is correct? Both the dimension have, we know that. So what is the answer? So you got to use the formula dimension of V1 plus V2. So dimension of V1 plus V2 should be dimension of V1 plus dimension of V2 minus dimension of the intersection V1 intersection V2. Now what you will get? This should be, we know that is 19 plus 70 minus, we don't know this value. So dimension of V1 intersection V2. And what is this? 36 minus dimension of V1 intersection V2. And we know that V1 intersection V2 is a subspace of R4. Intersection of two subspaces also subspace. Sum also subspace of R24. This is subspace of R24. Since this is subspace of R4, therefore what is the dimension of V1 intersection V2 is less than or equal to 24. Maximum is 24. Okay, V1 intersection V2 should be 24, less than or equal to 24. But here we need a minus dimension. Therefore multiply minus, we get minus of dimension of V1 intersection V2 should be greater than or equal to minus 24. Therefore here we can replace this is equal to greater than or equal to 36 minus 24. So this should be 12. I'm writing, I'm right? Yeah, if you sum this one. Okay, otherwise we cannot say, okay, because here the C option says at least 19, therefore this is not true. So maybe you can take intersection, you can take intersection this side and then sum that side. So same formula will work, right? So dimension of V1 intersection V2 equal to dimension of this same thing. So now what can you say about that one? Okay, dimension of V1 intersection V2. Again take this dimension of V1 intersection V2 this side and then take this to this side. The same thing will get equal to 36 minus dimension of V1 plus V2. Okay. So again V1 plus V2 is a subspace of this. So should be less than or equal to 24. Therefore greater than or equal to 24. Therefore is greater than or equal to 12. But more than greater than 2, therefore we can say 2 is also 12 also greater than or equal to 2, we can say. So we can say the first one, but what can I say about the upper bound for this one? I think this is not a multiple choice question. Okay, so
There's a formula we can use for this, sir.
Yeah, we can use the formula. So dimension of what is the formula? Union, not union.
Dimension of V1 W1 plus W2 is less than or equal to minimum of dimension of W1 plus dimension of W2 comma dimension of V, sir.
Okay. So actually okay, so you are saying dimension of sum
Yes, the sum of the subspaces
is less than or equal to,
is
or
less than or equal to minimum of sum of the subspaces and dimension of the space vector space, sir. Comma dimension of V, sir.
okay, here V is 24 because this subspace, therefore maximum is 24 or less than or equal to this. Yeah, so therefore this is actually what is the sum, 36 and this is 24. So from this what can you say, minimum is 24, therefore less than or equal to 24, then this is trivial always. So
And
from
it's
this
greater than or equal to maximum of these dimensions, sir.
greater than or equal to maximum of this,
Maximum of dimension of V1 and V2, sir. Dimension of V2.
so there should be what 8 19 and 17,
19,
maximum
sir.
19. So okay, so therefore C, you are saying C, okay, because it
Yes, sir.
satisfies C1. Okay, okay, the next one is correct. Answer is greater than or equal to 19. Okay, the next one, I think 5th or 6th something. Suppose V1 equal to the vector 1 2 0 3 0 is an element in R5, and V2 is another element, is an element 1 comma 2 comma minus 1 comma minus 1 comma 0, and V3 is 0 0 1 comma 4 comma 0, and V4 is 2 comma 4 comma 1 comma 10 comma 0, sorry, comma 1, and V5 is 0 0 0 1. They given 5 vectors. Now the span of these 5 vectors, span of V1, V2, V3, V4, V5, all possible linear combination of this one, this is span. What is the dimension of this span of the subspace is? So first option 2, 3, 4, 5. So you have to find the linearly independent set among these 5, the independent set. So what is the independent? All 5 are linearly independent or anything. So how to solve this one? So you have to take the linear combination of all the things, alpha 1 into the first one, alpha 2 into second one equal to 0, and then you try to solve this is 0 or not. So alpha 1 times V1 plus alpha 2 times V2 plus alpha 3 V3 plus alpha 4 V4 plus alpha 5 V5 equal to 0 comma 0 comma, that is 0. If you take this linear combination equal to 0, okay, so if you prove all scalars are 0 or not, so how to prove this one? So you have to form a matrix equation, right? So here alpha 1, if you substitute the values, you can write in the matrix equation. Here the unknowns are alpha 1, alpha 2, etc., alpha 5. So you have to write the V as a column, first column, okay. So then only if you multiply this you will get. So what is the alpha 1, sorry, V1 1 2 0 3 0, okay. So that is a V1. V2 is 1 2 minus 1 minus 1 0. So V2 is 1 2 minus 1 minus 1 0, and V3 is 0 0 1 4 0, and V4 is 2 4 1 10 1, and then V5 is 0 0 0 1, should be equal to 0 0 0. If you write in the matrix equation, you will get this one. Okay. Anyway, this is same as this one, because alpha 1 times, if you write the V1 plus alpha 2 times this one, and then etc. If you multiply this alpha 1, if you sum the first coordinate only, you will get this into this equal to 0. Okay. So we get a 5 equation, okay, 5 unknowns. So that equation, system of equation form in that matrix form. Okay. Now we have to apply row reduced echelon form. We have to find the rank of this matrix actually. So we have to find the rank of this matrix, because we need linearly independent. So this is the number of linearly independent columns or number of linearly independent rows we have to find. So therefore we have to apply row reduced echelon form of this matrix. Suppose we take A, and we have to find RREF, row reduced echelon form of this matrix, and then you have to find the number of non-zero rows in that row reduced echelon form. That is the rank of this matrix. That is the linearly independent set. Okay. So you can find that, you can apply row reduced echelon form anyway, so it will take some time. So you will get the number of non-zero rows is 3. So therefore there are 3 linearly independent set. So therefore the span of the dimension should be 3. Okay. So this is a method. You have to form the matrix, and then you have to reduce, we have to find the rank of the matrix. So you simply can reduce the row reduced echelon form, and then find the number of non-zero rows. So that is a rank. So the number of rank is nothing but linearly independent or dimension, because row rank equal to column rank equal to this, because the span of this nothing but, if you look at the span, so what is the definition of this span? If you look at this, you will get same thing, alpha 1 V1 etc. alpha in Vn, alpha is our okay. Now the next question is simple one. Suppose we have a set in R2, that is set of all x comma y in R2, such that the product is greater than or equal to 0. So simple one, they are asking is the vector space or not. V is a vector space over R. Sorry, vector subspace. Anyway, it is a subspace of R2. Vector subspace is a subspace of R3. R2, R0. The first one. Second one is not a vector space, not a vector subspace of R2, since every element does not have an inverse. They say the reason, since every element does not have an inverse, that's why it is not subspace, does not have an inverse in V. Third option, it is not a subspace, not a subspace of R2. Reason is since it is not closed under scalar multiplication. Since it is not closed under scalar multiplication, closed under scalar multiplication. And then vector addition is not closed under vector addition, that is the last option. What is the reason it is not subspace, or you claim that this is subspace? It is not a subspace of R2, since it is not closed under addition. It is not closed under vector addition. Vector addition, okay, actually. So what is the reason, and which one is the correct answer? So already we know that actually every subspace in R2 is nothing but is line passing through origin. any line passing through origin are the only subspace in R2. Okay, that is a simple thing. But this is not a line. So xy is greater than 0 is union of two quadrant. Either both x and y are negative, the product is positive, or both x and y are positive, then the product is positive. Therefore, this V is nothing but union of the two quadrant. So what are the quadrant? So here in the first quadrant both x and y are positive, and here x is negative but y is positive, and here both are negative, and here x is positive, y is negative. So therefore, the given space is nothing but union of this portion, this quadrant as well as this quadrant, the first and the third. This is not a line. So I already said that. So the subspace R in R2 is nothing but just a line passing through origin. This is a plane. Actually, it's not a plane actually. So this is this portion. Therefore, clearly it's not a subspace. Therefore, first option is not true. But what is the reason? They say the second option says does not satisfy inverse. So in the subspace we are not going to check any inverse of the vector. Okay, so that is not true. It's not closed under scalar multiplication, or it's not closed under vector addition. So what is your guess?
And it's not closed in the vector addition, sir.
No, why? Suppose you are taking,
Because if we take minus 4 and minus 2, sir.
Okay.
And 2 and 4.
Okay. If you sum this, you get minus 2 comma 2. Right? The product is not positive. Therefore, it's not closed under addition. Okay. What about scalar multiplication? It's always positive.
It is not closed, sir.
Yeah, it is not closed. That is the reason. But it's closed under multiplication. Why? Because suppose if you take some xy and multiply with alpha times xy, so this is nothing but alpha x comma alpha y. If you product this alpha square xy, so anyway, if it is always greater than 0, because already we know that xy is greater than 0, alpha is anything, so always. Therefore, it's a subspace. It's not a subspace because of it's not vector addition. Yeah, correct. That is the correct answer. Okay. So the next question: orthogonal trajectories of the family of curve. So 7th question: the orthogonal trajectories of, so the orthogonal trajectories of the family of straight lines. What is a straight line? The family y equal to k times x minus 1. Here k is any real number. That's why it's a family. If k varies, we will get so many equation, line equation. That is a family. We got to find that orthogonal thing. So the first option, so should be circle x minus 1 whole square minus y minus 1 whole square should be equal to c square. So already we solved this problem, I think so. So b is x square plus y square equal to c square, and then x square, everything is a circle. The only thing is the center is changing. So this is c, and the d option is x minus 1 square plus y square equal to c square. So what is the orthogonal trajectories? Okay. So how to find this one? You have to differentiate the given differential equation. So given equation is y equal to k into x minus 1. You have to differentiate both sides. Therefore, we get y dash equal to k into, if we differentiate x minus 1, we get 1. So therefore, we get this one, and we have to replace y by minus 1 by y dash this is equal to k. So therefore, what is y dash? Y dash equal to minus 1 by k, but replace the k value. K is nothing but y by x minus 1. Therefore, we will get, what will get? Minus of x minus 1 by y. Okay. So that is thing. Now apply the change of variable. So this is dy by dx. Dy by dx equal to minus of x minus 1 by y. Just to cross multiply, we get y into dy equal to minus of x minus 1 into dx. So if you differentiate this, we get y square by 2, and here if you integrate, if you integrate this side, we get minus of x minus 1 whole square by 2. By some constant, we can take some c square. Therefore, you can multiply by 2, and this is a circle of center 1 comma 0. So the last option. Okay, x minus 1 square plus y square equal to c square is the orthogonal trajectories of this one. Okay. Okay. So next question. What is the center of the group? Okay, unknown is 8th question. Suppose in the group integers, set of all integers with respect to addition is a group, we know that. The subgroup generated by 2 and 7 is, what is the subgroup? The first one is Z, second one is 5Z, because every subgroup of the form NZ, but it should be generated by 2 and 7. So that is contains 2 and 7. So clearly, which of the following subgroup contains 2 and 7, and also is generated by 2 and 7. So we can omit the second option and then third option, because both subgroup does not contains 2 as well as 7, because the second group is all multiples of 5, 0, 5, 10, 15 and so on. This does not contains 2. Therefore, we can omit B and C. Now, what about the last option and then first option? So anyway, both contains 2 and 7, but should be, but here also is not contained, right? So because because this everything is a multiple of 14. Therefore, 0 plus or minus 14 plus or minus 28 and so on. So actually, what is the meaning of the subgroup generated by 2 and 7? We can write the notation this 2 comma 7. So that is all possible linear combination, that is 2 times some n plus 7 times m, where n and m are varying in Z, right? That is a subgroup generated by, suppose if it is subgroup generated by only one element, means what? All multiples of 2 you are taking Z. 2 means what? 2 times n plus 7 times m for all m. If you take m equal to 0, this term cancel, n equal to 1, we get 2. So 2 should be in the set. Similarly, if you put n equal to 0, m equal to 1, we get 7. Therefore, 2 and 7 should be in the set. So we can easily eliminate all other options. So we can easily check that should be Z. Okay. So should be GCD of, actually GCD of 2 and 7. That is the thing. So therefore, Z is the only subgroup generated by 2 and 7. Okay. So the next one. Next question. Any doubt in this? Okay. So what is the cardinality of center of the group? The cardinality of the center of the group. So we know what is the center. Okay. So center of the group is at 12 is the first option 1, 2, 3, 12. So Z12, what do you know about Z12?
12.
12 is the correct answer, is 12, because we know that if G is Abelian, if G is an Abelian group, if and only if the center of the group equal to the given group for any group. So here Z12 is Abelian group, therefore center of Z12 should be Z12. Therefore the cardinality of this one is nothing but cardinality of this should be 12. Therefore answer is 12. Okay. Now the next one, maybe almost we solve these problems. Okay, maybe I solve one problem and then we can stop. So 10th problem. So what the problem is, suppose T is a linear transformation from Rn to Rn. It is given T is a linear transformation from Rn to Rn. Be a linear transformation is given, and is also given that is not 1-1 function, is not 1-to-1. Then which of the following is true? So the first option, rank of T should be positive, strictly greater than 0. Second option, rank of T equal to n. And then C, rank of T is less than n. So rank of T is nothing but the dimension of the range space, strictly less than n. And then the last option, rank of T is should equal to n minus 1. So what can you say about this? T is a linear transformation from Rn to Rn, but is not 1-1. If it is 1-1, then kernel should be 0, but it is not 1-1. Therefore kernel contains at least one non-zero element. Okay. Now by rank nullity theorem, dimension of the domain is n. So n equal to the null space of T plus the rank of T. Okay. So we know that the null space contains at least one, but we don't know how many, what is the number of dimension of the null space, but dimension, the nullity of this one at least 1 is greater than or equal to 1. Therefore what is R of T? Equal to n minus the null space of T. Therefore should be what? Cannot say this is exactly 1. So therefore this is less than or equal to n minus 1. Right?
Yes,
so
sir.
Therefore what can you say? What is the answer? Sometimes equal or sometimes strictly less than.
C, sir.
Yeah, we can say it should be strictly less than n, because we cannot say equal to n minus 1. Okay. So or if it is maybe okay, yeah, maybe depending upon the linear transformation we can say the dimension of null space, therefore should be less than n, we can say. Okay. Okay, anyway we can stop now.